I want to try to do the next two modules kind of all in one sitting, and then I'll just upload the videos separately. These are both relatively short, and they're both things you've seen before. I want to briefly talk about the Pythagorean theorem. That's something that you're going to keep needing all the way through calculus. And then we're going to talk about trig functions, which you've already seen before, and in geometry we use them in a quite specific way. And then once you get into your senior year, you'll have more with trig functions and look at them in a different way, but sometimes it's still very useful to come back and sketch out a triangle. So we'll talk about it right now just from the triangle perspective. I've seen proofs of Pythagorean theorem. Well, they're supposed to be proofs as a picture, I guess, that have like the c squared coming out this side and b squared coming out this side, and they kind of make the argument that it's the same number of units. But to me, that feels not quite proofy because it's got only exact units. It's only Pythagorean triples. So a Pythagorean triple is when they're all integers, like 3, 4, 5. So I want to look at it from a more general point of view and consider it algebraically. So the first thing I'm going to do is I'm going to take this triangle, so you can see now C is the hypotenuse, and I'm just going to rotate it. And then if I add 3 more copies identically of this triangle, then you can see that the entire area represented here is C squared. So that's the part I wanted to get there. So I'm going to snag that and open chalkboard and move this and move that. Okay, so this is what we're looking at. That is my cat playing with a toy, if you heard that. Okay, so this is what we have, and this is all c squared. So I want you to look at individual triangles, which you've learned in the past, I feel sure, that the area of a triangle is 1/2 times AB, and we will study that ourselves, but the reason is that this is for right triangles only. A right triangle is half of a rectangle. The area of this is A times B, so half of it's here and half of it's there. So the triangle itself is 1/2 AB. So between these, oops, let me make a little copy of this over here. One, two, three, four identical triangles. So from these 4 pieces, we have 4 times 1/2 AB. So we have 2 AB. Now, this little square in the center, if you look at this piece, this is A minus B, okay? Because we have A on this side, B, this part's B, and we're left with this part. So A minus B. So that little bit in there is A minus B squared. So A minus B squared plus the 2AB that we got from those triangles makes the whole, and the whole is C squared because it's a square with C on either side. So if I FOIL this out, I get A squared minus AB plus B squared plus 2AB. So that's all C squared. So A squared minus 2AB plus B squared plus 2AB. So this stuff all cancels. And this is where you get A squared plus B squared equals C squared. When you get into pre-calculus, you'll have a more general rule about how to find these things when it's not a right triangle, but this is what it is right now, and we're only going to look at right triangles for this part. Okay. So that gives us the Pythagorean theorem. And the other thing that we get with right triangles, or really anything with an angle, but the sine, cosine, and tangent, which are three of the trig functions that you'll deal with, until you're out of math, really, those have a special situation when it's a right triangle. So this is only if it's a right triangle. So if this were an angle, theta, then over here we would call this the opposite side. It's the one it kind of opens its arms to, right? So opposite over here. This one's the hypotenuse, and that's the thing that makes it, well, that's one of the things that makes this special to a right triangle. When we use the word hypotenuse, we're by definition stating it's a right triangle and this is the longest side. So this is always the hypotenuse. It's always the one across from the right angle. And this one we call adjacent. So both of these are adjacent to theta, but this one's the hypotenuse. So that's how you decide which one's adjacent. It's the guy next to him that's not the hypotenuse. And so what you get is the actual functions are sine, cosine, and tangent. In a calculator, they look like sin, cos, and tan. But it's sine, cosine, tangent. And the phrase that people use generally to remember is SOHCAHTOA. So sine of theta is the opposite side divided by the hypotenuse side. Cosine is the adjacent side divided by the hypotenuse side. And tangent is the opposite over the adjacent. Now, in real life, tangent theta is defined to be sine theta over cosine theta. So that, for us, in these right triangle situations, is opposite over hypotenuse over adjacent over hypotenuse. So you invert and multiply, you get opposite over hypotenuse times hypotenuse over adjacent. The hypotenuses cancel, and you end up with opposite over adjacent. So that's what makes that so. But we can use this then sometimes to solve for a side using our calculator, which has the sine, cosine, tangent function. So if I had, for example, that this was 25 degrees, and I knew that this side was 7. Okay, this is going to be a horrible number because I'm making these up, and this isn't a nice number in either case. So let's say I knew that was 7, and I wanted to know the rest of the triangle. Well, if I have two sides, I can use the Pythagorean theorem, and that oftentimes is the fastest thing to do. But I don't have two sides, I have one. But I do know that this is opposite 25. And so I can either solve for adjacent or hypotenuse. It doesn't matter, it's up to you. Need to remember to stay above that little line there. So if I want to solve for hypotenuse, then I have to say to myself, I have the opposite, I want the hypotenuse, so the guy I want is sine. So, SOHCAHTOA. If I want to solve for the adjacent, then I've got opposite, I want adjacent. Opposite and adjacent is a tangent issue. So let's just try to solve for adjacent. So what we would write is tangent of 25 degrees equals 7 over adjacent, which you might name something else. So then A times tangent 25 degrees is 7. So then I would divide by tangent 25 degrees. Okay, so I've just cleared myself some room now. So A equals 7 divided by tangent 25 degrees. So that equals okay, so that's approximately 15. It's 15.01, so we're going to say it's about 15. So now I have 15 over here. So then to solve for the hypotenuse, if I want to solve for the entire triangle, I would just say 7 squared plus 15 squared equals c squared. So I'm always going to end up taking the root. So the square root of 49 plus 225, which is the square root of 274. That's 16.55. And now we have the whole triangle. Okay, so you could do a couple of more examples. I suppose I can just clear this. And let's say instead that you had um, 65 degrees here, and you knew, say, the adjacent. So let's say that you knew this was 9, and you want to solve for the whole triangle. So you know the adjacent one. Let's say that this time you wanted to solve for hypotenuse first. So you would say adjacent over hypotenuse. So cosine of 65 degrees is the adjacent over the hypotenuse, and let's call this y and this x this time. So that's 9 over y. So y times cosine 65 is 9. So that is, really should have brought a calculator over here. Ignore me for a minute because I don't want to waste too much time deleting these pieces out of here. I'm having to translate to radians, which we'll actually get to in the next mod, because the calculator I'm using doesn't use degrees, because degrees are a nonsense measure, which I will also get into in the next mod. So we had 65, and there is an easy way to convert them, but for the moment, I'm going to go over here. We've got 9 divided by cosine. So 21.3, basically. So now we know we have 21.3 and 9. The reason I'm resketching it now, and you don't have to, you could just write 21.3 over here, but I want to make it clear. Now the one we have is the hypotenuse. So we don't want to just go through and write, oh, the other side's the square root of 9 squared plus 21.3 squared, because this is the one on the other side. So 9 squared plus x squared, remember I named that x, is 21.3 squared. So we have another step here. We need to say x squared equals 21.3 squared minus 9 squared. And then we'll take the root of this. 19.3. So our complete triangle is 19.3, 9, 21.3. Okay, so do one more of these and then talk about how to use this. And this time, of course, I'll use one with sine. So let's make the upper one the one we know this time. So let's say that's 50. And let's say that we know the opposite is 8. And so this time, instead of using tangent and finding adjacent first, we'll use sine and find hypotenuse first. So y, x, sine of 50 degrees is opposite over hypotenuse. Y times sine 50 equals 8. So this is how we solve for y. That's going to be 10.4. Okay, so we have 8, 10.4, and we need this one. So 8 squared plus x squared is 10.4 squared. X squared is 10.4 squared minus 64. And that's 6.6. And that's how we find the triangle. So the very, 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 very common uses of these things is to find the length of a ladder sliding down, the length of, or the height of a lamp post by measuring the shadow and the angle of elevation. Those will come up more in pre-cal too. Once you get into calculus, you start getting things where you've got, a boat that's attached to a dock and it's gone off at an angle and things like this. But for right now, we're going to stick to a kind of short version of the lamp posts and the ladders and things like this, because you are going to get the rest later. Okay, so if the question was about, say, a ladder leaning against a wall, it would say something like this. There's a 10-foot ladder leaning against a wall, and you want to know the height a person will actually be if they climb the ladder. This is not how they usually ask this, but we're winging it. So if a person climbs the ladder, how far up will they be? Maybe you're trying to get to a certain height to paint or clean a window. And so the 10-foot ladder's there. and you're given, say, this angle, which you could fairly easily measure from the ground. So this angle is given to be, say, that looks pretty big, 60. Let's say that one's 60 degrees. And so you want to know how high on the wall are you if you climb the ladder. So in this case, instead of solving for an entire triangle, the only thing I really want is this side. So I'm not going to have a lot of decision making to do about which trig function to use. I've been given the adjacent because this is the ladder. Not the adjacent, the hypotenuse, because this is the ladder. This is the right angle, unless the building's crooked, which we assume it's not. So I'm given the hypotenuse. I want the opposite. So I'm going to use sine, because that's the thing that relates those two things. So sine of 60 degrees is going to be the opposite, which I've named h for height, but you could name it something else if that bothers you because of hypotenuse, divided by 10. So to solve for h, I just do 10 times sine of 60 degrees, which is 10 times square root of 3 over 2. So whenever you put this in your calculator, whatever this is, that's what the side is. .66. So if you were looking to be 8 2/3 feet, or 8 foot 8 inches up the wall, then you'd have the ladder in the right place. If not, you might pull it out or shove it up and measure again. Okay, so if we were asking a question about a lamppost, it might say, there's a lamppost, and maybe you want to know how far away from the lamppost is this spot on the ground, because maybe you're considering going there later and sitting and studying, and you want to know how much light you have. And so you want to know not this distance, because you can just measure that, but you want to know how far you are from the light itself. And that is more difficult to measure. So you measure this, and let's say that that distance is 12. And let's say that you can basically point from here to the light and you can measure this distance. So you've just done something where you've angled toward it, and so you measure this, and this is, say, 30. So if we extend this out, it's still 30. I'm having a lot of trouble with this one. Okay, so that line, this is still 30, and your distance in this case is the hypotenuse. And so the thing you're looking for is the hypotenuse, and we can name it x if you want. So this distance is adjacent. So you have adjacent, you want hypotenuse, and you ask yourself which trig function relates adjacent and hypotenuse. So TOA, so cosine 30 degrees equals 12 over the hypotenuse. So hypotenuse, and we can call it x, of cosine 30 is 12. So dividing by cosine 30, we get 12 divided by cosine 30. Cosine 30 is also the square root of 3 over 2. So x is 12 divided by the square root of 3 over 2, which is 12 times 2 over square root of 3, which equals 24 over root 3 . Okay, 24 over root 3. Should you want to rationalize it, you'd get 24 root 3 over 3, which is 8 root 3. You can put either one of these things in a calculator, you're going to get the same thing. The only reason I'm even mentioning rationalization, because actually rationalization of fractions goes way back to when people used slide rules, which I can show you one, but on a slide rule you had some of the main square roots, and so you could look them up. And if you look up, say the square root of 2 is 1.414, it's easier to multiply that by 8 than to divide 24 by that. So people who are doing it in their head also would want to rationalize. But since nobody uses a slide rule, unless you're going to be in a job where you need to very quickly know square roots in your head, this is just as good as that, and there's no reason to be still doing it. But anyway, we have 8 times square root. Oh no, it's divided this time. Oh no, it is times. 24 was divided, 8 is times. 13.86 or 13.9. So your distance from the lamp is 13.9. Okay, so I want to move on to one last thing, and then probably I won't get that other video right this second, but maybe I'll do it tomorrow, or maybe I'll do it tonight, but I'm not thinking clearly enough, I don't think, to continue. So what we want to talk about besides these little trig applications, which we're not going to have very many problems on, is special triangles. And special triangles, there are two of them really, but you consider a couple of things about one of them. There's the one where, oh my goodness, these are the same and these are the same, so 45, 45. So the 45, 45, 90 triangle is one of our special triangles, and that has a 1:1 ratio on these sides. So Pythagoras would tell us the square root of 1 squared plus 1 squared is this side. This is square root of 2. So that's pretty straightforward. You know, if these are 45, then these are the same. It's an isosceles triangle because these angles match. So we've just talked about that. So hopefully you remember that. So 1:1 root 2. The other one that we care about is the 30, 60, 90 triangles, which is why when I got 30 and 60 in the previous problems, I didn't go punch it in or look it up, because we want to memorize actually the special triangle relationships. And so you might think I'm going to say 1, 2, root 3, but it's actually not the case. So it turns out on a 30, 60, 90 triangle that the relationship goes 1, 2. The hypotenuse is the 2. So 1 squared plus this squared is 4. So 1 plus 3 is 4. This side is root 3. And that's why that was showing up. So these are the ones that we kind of want to memorize. So if you remember how to build the triangle, and there's another way that has to do with your fingers, which I can show you in real life. I don't know about doing it here, because you're going to need to really have these down, you know, your senior year, basically. So 1, 1, this you should get for free from knowing it's isosceles, right? These are the same. Root 2. So what that means is, if you saw a triangle that was, say, 5, 5, then this would be 5 root 2. But as far as sine, cosine, tangent, sine of 45 degrees is opposite over hypotenuse 1 over root 2. It's usually given as square root 2 over 2, again because of that rationalizing the denominator thing. So these are both 45. We'll get the same result in either case. Cosine 45 degrees, well, the adjacent's the same as the opposite, so this is actually the same. So sine and cosine both square root of 2 over 2. Tangent being opposite over adjacent, tangent's just 1. So sine and cosine both root 2 over 2 for 45 degrees. Tangent 1 for 45 degrees. So this is one of the sets of numbers that you need to note and memorize. I'll fix that little triangle in a second. Okay, so for this one, they're going to be a little different, but they're related. So anytime you have two angles that add up to 90, one of them's sine is the other one's cosine, because like this guy's opposite is this guy's adjacent. This guy's opposite is this guy's adjacent. So you're always going to have repetition between values that add up to 90, because they'll always be partners in a triangle, in a right triangle. So in this particular case, sine of 30 is opposite over hypotenuse 1/2. Cosine of 30 degrees, adjacent over hypotenuse. There's nothing to rationalize now because the hypotenuse is a whole number. Tangent, 30 degrees, is opposite over adjacent. So this is the one that has to be rationalized. So over here, sine of 60 degrees, opposite over adjacent. So these match. Cosine, 60 degrees, 1/2, adjacent over hypotenuse. Tangent of 60 degrees is opposite over adjacent, so square root of 3 over 1, which is just root 3. So tangent in this case, 1 over root 3 or root 3 over 1. So this is where square root of 3 will show up a lot in these special triangles. And so this is another thing that you need to have memorized. Let me see if I can draw the finger thing. If I was in a quadrant, if I go up, you know this is 90 degrees. So here's an angle that's approximately 30 degrees. 45 degrees there. And 60 degrees there. So you imagine this are like fingers. Okay, so basically, whichever one you're doing, so by the way, an angle of 0, the opposite is 0, so sine of it is 0. The adjacent is 1 if it's a unit. So this has sine 0 and cosine 1. And this has the opposite, because this time it's the adjacent that's 1. The opposite is 0. But we're focusing on these three here, right? So the way it goes is square root fingers over 2. That's the mnemonic. So if I'm looking at 30 degrees, then this is the finger that I would bend in. So like in real life, you would put your index finger down for 30. And it's square root fingers the top fingers are cosine, the bottom fingers are for sine. So this is in alphabetical order if you want. So cosine, sine. So cosine of 30, because it's the top part, comes first, is square root, I have 3 fingers, over 2. And sine of 30, I just have 1 finger, so square root 1 over 2, which is 1/2. Okay, so let me... Oh, that was odd. Okay, so now I put the fingers back. So now if I move up to 45 degrees, this is the one that I would bend down. So now you see in both cases I have 2 fingers. So both functions are square root of 2 over 2. Square root of fingers over 2. Okay, so now I put my fingers back. If I go up to 60 degrees, it's this guy. So this is the one I bend down. Cosine is now square root 1 over 2, which is 1/2. And sine is square root 3 over 2. So it's the opposite of this one, as we learned it was before. So this little finger trick is one way to remember if you get stuck. You can always put it into your calculator. Of course, you might not recognize square root of 3 over 2. But this is just an easy little trick for you to kind of remember if you're in a panic or on a test or something. So anyway, I think, as I said, that I will do the circles later. I was going to do them now. I kind of want to talk about radians and why degrees is a nonsense measure, but I think I will just do that a little later. So I'll post this as quickly as I can get it to upload, and in the meantime, I'll work on an assessment.